Ever wondered what's really going on in an examiner's head when they're marking your exam paper? Well, today, we're pulling back the curtain. We're going to take just one AQA GCSE Physics question and break it down step by step using the official mark scheme. This isn't just about finding the right answer. It's about understanding the game so you can get every single mark you deserve.
Okay, let's get into it. Here's our game plan. First, we'll introduce the exact question we're going to be cracking. Then, we'll go for the quick wins, the definitions and equations that get you easy marks on the board. After that, we'll dive into the calculations and show you exactly how to lay out your work. Then, the big one, the 6-mark answer. And finally, we'll wrap up with the key takeaways that you can use on pretty much any exam question.
Right, so our focus is question 3 from the AQA GCSE Physics Paper 1, the higher tier paper. It's a really good one to look at because it actually mixes two totally different topics, electrical circuits and changes of state.
So here's the circuit diagram that comes with the question. What we've got is a 12-volt battery that's powering a few heating elements, and you can see they're all hooked up in parallel. This is pretty much how a heated car windscreen works to melt ice, which you'll see is exactly what this question's all about. Let's start by banking some of those foundational marks. You know, the first parts of a question are often there to test your core knowledge. They're designed to be quick wins, to build your confidence, and to get you warmed up for the tougher stuff later on.
First up, question 3.1. It's a 1-mark definition. What is meant by direct potential difference? This is pure memory recall. You can think of it like water flowing in a river. It only ever goes one way. That's the basic idea. But what's the exact wording the examiner is looking for?
And here we go. This is the perfect answer, taken straight from the mark scheme. You get 1 mark for saying the polarity of the potential difference doesn't change. Now check this out. This is the really useful bit. It says, allow, direction of the potential difference doesn't change. This is a great insight, right? It shows the examiner isn't looking for one single magic phrase. They'll accept different wording as long as you've got the main idea down.
Moving on to 3.2, another 1-marker. This time, you just have to pick the right equation from a list. You just need to know which one connects charge flow, energy, and potential difference. And the correct answer is E equals Q times V. Energy transferred is simply charge flow multiplied by potential difference. That's a nice, easy mark for knowing your way around the equation sheet.
Okay, with 2 marks in the bag, it's time for the calculations. And listen, this is where showing your working is absolutely non-negotiable. You can actually get marks for the right steps even if your final answer is wrong, so never ever just write down a number by itself.
Here's the first one, 3.3. So we're given the energy, 15,000 joules, and the potential difference, 12 volts. Our job is to calculate the charge flow. We literally just picked out the equation we need, so now we just have to put it to work.
To get all 3 marks for this, you have to show these 3 distinct steps. The first mark is just for putting the numbers into the equation correctly. 5010 equals Q times 12. See, you get a mark even if you mess up the math later. The second mark is for rearranging the equation correctly to find Q. And the final mark, that's for the correct answer.
The correct answer is 417.5 coulombs. And hey, look at the mark scheme note again. They also allow 418. This shows they're a little flexible, but it's always best to give the exact answer from your calculator just to be safe. Next up, question 3.4, and we're switching gears from electricity over to thermal physics. We're using that same amount of energy, 510 joules, but this time it's to melt 0.015 kilograms of ice. We need to find the specific latent heat of fusion.
And guess what? The process here is identical and so is the marking. We're using the equation energy equals mass times specific latent heat, or E equals ml. Once again, you get 1 mark for plugging the numbers in, a second mark for rearranging it to solve for L, and that third and final mark is for getting the calculation right. See the pattern? It's a recipe for success.
And when you do the math, you get an answer of 334,000 joules per kilogram. By following those clear steps, you've just bagged another 3 valuable marks.
All right, here we go, the main event, the 6-mark extended response question. This is where you have to build a proper, logical explanation. Now, I know they can look a bit scary, but they are so manageable once you know what the examiner is looking for.
The absolute key here is to pull the question apart before you even write a single word. It asks you to explain the changes in the arrangement and movement. See that word "and"? That's a huge clue. You must talk about both things to get top marks.
And it covers two stages. First, the ice melting, and second, the water warming up. A top-tier answer has to cover all of that. Now, this is the secret sauce. This is the examiner's checklist, or what they call indicative content. It's basically a list of all the points they want to see. They want you to talk about solids having a regular pattern and vibrating, and liquids being random and moving freely. You have to mention that during melting, the temperature doesn't change because the energy is increasing the particles' potential energy. Then as the water warms up, the particles move faster, so their kinetic energy increases. And for a bonus, linking it all together by saying internal energy is just the total of both is a really high-level point. A 5 or 6 mark answer will weave a bunch of these points into a clear story.
Let's just zoom in on the most important comparison here. As the ice melts, you need to clearly explain the change from solid to liquid. In the solid, particles are locked into a fixed, regular pattern, just vibrating. But in the liquid, they've broken free. They're in a random jumble and can move past each other. Nailing this contrast is absolutely fundamental for a good answer.
So we've completely deconstructed question 3. But what are the bigger lessons here? What can we learn about exam technique in general? Let's zoom out and pull together the key strategies we've learned from looking at this mark scheme.
Okay, here are the crucial takeaways. First, get familiar with how mark schemes work. Look for those allow comments that show you where there's some wiggle room. Second, for any calculation, show every single step: substitution, rearrangement, final answer. Third, for those long answers, use the right scientific language. That indicative content is your best friend. And finally, and this is probably the biggest one, just answer the exact question they asked. If it asks for 2 things, you give them 2 things.
And that's our deep dive into the mind of an examiner. We've seen exactly how they award marks, from simple definitions all the way to those complex explanations. So, I'll leave you with this final thought. Now that you've seen inside the process, now that you know how you're being marked, what are you going to do differently in your revision?